Hi people, morning. You're doing good. We have only four of us, four of you. Wait for maybe 2 3 more minutes. Yeah. Good morning. We'll just wait for 2 3 more minutes. Let your friends join. So, is any update from your schools? When are they going to open? Any such thing they have told to you?
No, sir.
No. So, what chapters going on in your schools now? Chemistry. Which chapter is going on?
Organic first lesson.
Sorry.
Hello, alkenes.
Halo alkanes. Okay. Before that, have they completed any chapters? Before that, halo alkanes, haloarenes?
Solid states and solution.
Solid state and solid state completed. Okay. So, what about the other sir? Like, has he
Electrochemistry.
completed? Electrochemistry also completed.
Yes, sir.
Okay, good. Yeah. So, what about the other sir in Epsilon? Like, has he completed alcohol, ethers, phenols?
Yes, sir. He started aldehyde yesterday.
Aldehydes and ketones. Good, nice. Okay. So we still have electrochemistry, and I'll be taking solid states, chemical kinetics, coordination compounds. So, and maybe even inorganic chapters I'll be taking. Other than the organic chapters, I think that's all will continue. So maybe for us to meet offline, I think it will take another 2 months, maybe. Right. Until then, these online classes are going to continue. Okay, I think in 1 more minute we'll start, guys. So, did you write a test on what is in the two chapters are completed? That is haloalkanes, haloarenes, and alcohol ethers phenol. Did you write a test from Excellent Academy? I'm asking. Did you write a test?
He finished the lesson day before yesterday, so we still did.
Okay. What about the first chapter, haloalkanes, haloarenes? That was completed a long time, right?
Yes, sir. Test
You
completed.
didn't write a test. Sorry, Ms. Satyapriya, you're telling something.
It is completed for the first chapter, sir. Haloalkanes and aldehydes.
Oh, you wrote the test already.
Yes, sir.
Okay, good. Nice. Fine, guys. I think we'll start. Let me share my screen. So maybe before we start, we will just see what and all we saw last class. We have to write something. Yeah. Okay, so we were solving this thermodynamics of what is that? Electrochemistry. So we took the concept of this Kc, like you can see here, right? That we write generally as delta G is equal to delta G naught plus RT ln Qc, right? So when the reaction goes to equilibrium, I told you that delta G will not be there, only delta G naught exists. So now I'll be able to get a beautiful equation connecting my Kc and delta G, right? And I know delta G naught, again, is connected with your NFE naught, right? Delta G naught is equal to NFE naught. And then you will be able to get this particular equation if you connect these two, right? 0.059 by N into log of Kc. And obviously this will happen only at 25 degrees Celsius. Okay, we have written here, NFE naught is equal to minus RT ln Kc. Kc is the equilibrium constant. right? And then we went on to solve some problems, finding out the log of cases and stuff. Nothing, normal problems which you have solved, except that I would have asked you to find, instead of finding the E naught for this particular reaction, I would have asked you to find log of Kc. You have to use the formulas. That's it. Okay. And then we went on to see, yeah, this kind of equilibrium constants, how it will change when I add or subtract, right? All these things we saw. And yeah, then we move on to the second part of the chapter, that is electrolytic cells. So before we move on to see electrolytic cells, there are certain rules you have to understand. We started with Ohm's law, right? We said that V is equal to IR. We saw out what is resistivity. It is also called as specific resistance, right? And then we went on to see what is this conductance. Conductance is one reciprocal of resistance, right? And I told you that the unit will be per ohm, or it is called as mho, or it is called as Simon. And we generally use only Simon, S. The symbol is S. Okay. Then we went on to see conductivity. Conductivity is also called as another name for conductivity, guys. What is it? The clue lies in the same page, where whatever I'm showing you, it says in the same page somewhere. The clue is there. So conductivity is also called as what?
Specific conductance.
Conductance, absolutely right. You call resistivity as specific resistance. So obviously conductivity can be called as specific conductance. Okay. And I told you that it is represented by the letter K, which is kappa, right? Which is nothing but the reciprocal of resistivity, right? And the unit is Simon per meter. Okay. Then we went on to see another term called as molar conductivity, and it is nothing but conductivity of certain volume of electrolyte. Obviously, it's all certain volume of electrolyte having 1 m concentration, right? So the formula is like this: lambda m is what is made molar conductivity, which is denoted by the letter K. I mean, formula is K by C. K is the conductivity, and C is the molarity, right? And then I told you that the conversions are very, very important, right? You will generally use the molar conductivity unit as Simon centimeter squared per mole or Simon meter squared per mole, right? So for all these cases, K, for example, in this case, if at all I wanted in Simon centimeter squared per mole, the kappa value, the conductivity value should be in Simon per centimeter, right? And obviously this will be in mole per liter, that is molarity, and into 1000. Same way, if I want in this term, the conductivity should be Simon per meter, and obviously I have to put 1000. Do not forget this 1000. If you forget this, that's it, done. The problem is wrong. Okay, then we went on to see how do you measure this conductance, resistance, resistivity, all these stuff. How do you measure it? I told you that you will be facing some problems, right? What are the problems we face, right? We face the problem of two things. One is wires, because we are using electrolyte. These are liquids, right? We will not be able to directly connect wires. And then second thing is we cannot use DC, right? Second problem can be easily come out, right? We can easily overcome this. If I use, AC instead of DC, I use AC, it's okay, right? So for overcoming this problem, that is wires problem, then we went on to see what is this conductivity cell, right? So conductivity cell is like a glass tube, a glass vessel, which contains two electrodes like this. And to that electrodes, I connect the wires, right? And in between this, I fill the electrolyte. Right, whatever I want to find resistance or conductance or whatever it is, I fill it with this. Okay. Now, this conductivity cell will have some length and this will have some area. And I told you that we will not be measuring them. No, we will not measure them. What we'll do is you first time, yeah, any questions? Okay. So first time, whenever using the conductivity cell, you have to find this length and area. And remember this L by A is what is called as your cell constant. It's called G star. Okay, L divided by A is what is made G star, is called cell constant, right? And then this, how will you measure it? Is you first time when you use it, you fill the conductivity cell with a solution whose resistivity, conductivity, everything is known. Okay, now the only formula which you have to remember is this: R into K is equal to G star. R is resistance, K is conductivity, and G star is the cell constant. Okay, so if you know the resistance and the conductivity of a particular electrolyte, if you use this, then you will be able to find this value G star and then you use it, and then you use it for a solution which the resistance or the conductivity is unknown to us. Okay, right? And then yeah, I think we solved some problems also, right, based on this. Okay, maybe we'll solve just one more problem before we move on to the other concepts. Before that, let me start the page. Okay, is there any question, guys, you want to ask me from the previous class? I hope everything is clear. Fine. So maybe we'll just take one more problem, but for that, 1 second. Just give me a moment, people. I'll be back in a minute. Okay, so the problem is like this. Okay, type on the question, people. Type on the question. Resistance of a 0.2 m solution. Resistance of a 0.2 m solution of an electrolyte. Resistance of 0.2 m solution of an electrolyte is 50 ohms, 50 ohms. And its specific conductance is 1.4 Simon per meter, right? Resistance is 50 ohms and the specific conductance is 1.4 Simon per meter. Okay, fine. The resistance of a full stop, after that you give a full stop. Next, the resistance of 0.5 m solution. The resistance of 0.5 m solution of the same electrolyte. The resistance of 0.5 m solution of the same electrolyte is 280 ohms. 280 ohms. Right. Now the question is, find the molar conductivity. Find the molar conductivity of the 0.5 m solution. Find the molar conductivity of the 0.5 m solution. Okay, I'll repeat the question, people. Resistance of 0.2 m solution of an electrolyte is 50 ohms and its specific conductance is 1.4 Simon per meter. Full stop. The resistance of 0.5 m solution of the same electrolyte is 280 ohms. 280 ohms. Find its molar conductivity. In the sense that you have to find the molar conductivity of 0.5 m solution. Okay, go for it. I'll give you maybe 2-3 minutes for you to solve this. It is exactly same as the last problem we solved. You just have to use this particular formula, R into K is equal to G star 2 times. And tell me the answer. Hope you all remember how to do the problem. I even gave the formula. I told you have to use it 2 times. First time, using the data, you will be finding this G star. And after finding G star, then you find whatever is required for the second time. Like the numbers are pretty easy. Calculation also should not be taking so much time, I guess.
Sir, is it 500 Simon meter square per mole?
500, maybe it can be correct, I guess. Fine. So, any other answers anybody has? One answer is 500. Same answer. Okay, good. Then we'll try to solve. Okay. So fine. So first we'll use the formula, same formula, R into K is equal to G star. So first we'll use it for the 0.2 m solution. Okay, for 0.2 m solution, R is this much and K is this much. So I can find G star now, right? So G star would be R, which is 50 into 1.4. So can I say it would be 70? Is it 70? Right? 5 into 14 would be 70. Yeah, correct. 70. 70 per meter. Okay. 70 per meter. Okay, done. So that's about G star. Now, second time use this 0.5 m solution. So again, I use R into K is equal to G star. Now you see R is given to us. This is for 0.5 m solution. So R is 280 into K, which we don't know, into G star. I found it as 70 per meter. So K would be basically 70 divided by 280, which is 1 by 4. 1 by 4 will be 0.25 Simon per meter. No issues. Okay, 0.25 Simon per meter. Okay, next. Oh, this is not the final answer. I need lambda m in Simon meter squared per mole. This is what I need because everything is given in terms of Simon per meter, everything, right? So now I have that formula is K by C and K should be in Simon per meter and it should be multiplied by 1000. So K value we just found out, which is 0.25. Concentration is here, that is 0.5 into 1000, right? So now this would be, yeah, I think this should be 500, right? So this, if it goes 0.5 times, so this would be 0.5 times. Okay, so 0.5 into 1000, which will become 500. Yes, answer is 500. 500 Simon meter squared per mole. That would be the answer to this question. Okay, very easy problem. Very, very easy problem. Like this kind of problem, if it comes, easily 2-3 marks, done. Okay, done. So this is what I just, this is just a, recap of what the previous class which we saw. Now we'll move on. Okay, so we now know about conductivity, molar conductivity, conductance, resistance, everything we know. Okay, now what we'll try to understand is effect of concentration with respect to lambda m. Okay, so if I change the concentration, right, if change the concentration, what will happen to lambda m? That we'll try to see. Okay, now from the formula itself, we'll be able to understand people. Formula is what? Lambda m is equal to K by, yeah, look at the formula. Lambda m is equal to K by C. Okay, so obviously if I'm going, or I'll write it again here, right? Lambda m is equal to K by C, right? So obviously if I'm going to increase the concentration, the lambda m decreases. That is from the formula, logically we can see, right? Now, what is the actual aspect? Why is it that when I increase concentration, lambda m decreases? Is the question now. Okay, fine. So people, please understand, if assume it like this, say I have a solution with me, I have two solutions with two electrolytes with me. Okay. Now say this is highly concentrated and this is say diluted solution. Okay. This is the first one is a highly concentrated solution and this one is a diluted solution. That means it has more amount of water, whatever it is. Okay. Now what you understand is there will be so much ion. Say for example, I'm talking about KCl solution. Okay, and both of them contains KCl. Say assume that this is say 1m, say this is 0.1m, something like that. Very less concentration, and this is highly concentrated. Okay, right. So now what you understand is if I'm going to have very, very high concentrations, what will happen is this K plus and Cl minus, K plus and Cl minus will be very, very, very close to each other. Or in the sense, not only K plus and Cl minus, K plus and K plus, Cl minus and Cl minus, everything will be very, very, very congested because I'm going to have huge amount of ions. Obviously, right? If the concentration increases means what? Obviously, I added more amount of KCl. More amount of KCl means more amount of K plus, more amount of Cl minus, right? Then you can ask me, sir, if there are more ions, right? If there are more ions, obviously the conductivity should improve. Correct, because these are the charge carriers, right? These ions which we have inside the solution are the charge carriers. They only is responsible. They only is responsible for conductivity, right? So please understand, people. The amount of ions is directly proportional to K. More and more amount of ions I have, more and more is the K. But please understand, if the amount of ions is one criteria, but the distance between the ion, or I would say the mobility, is more important than the amount of ions present. Mobility means the ability of the ion to move inside the solution. Okay, remember, mobility is directly proportional to K, and I can tell you that mobility and concentration are actually inversely related. Now you can understand why. If the solution is highly concentrated, the ions will be so much congested, right? So if they're so much congested, they will find it very difficult to move inside the electrolyte, right? By that, the mobility is decreased. So K value is decreased here. You can see if K value is decreased, the molar conductivity will also decrease, right? So it is not only the effect of concentration. If concentration increases, obviously lambda m decreases. But if concentration increases, mobility of the ions decreases, right? Mobility of the ion decreases, and that decreases conductivity value also. Okay, so there are two phenomena here. One is about the concentration change. According to the formula, you can easily see that I'm going to have decrease in lambda m if I have increase in concentration, right? And if I have increase in concentration, even though I have more amount of ions, the mobility of the ions are decreased. The ability of the ions to move is decreasing, right? And that will decrease the K value and thereby decreasing the lambda m value. That is molar conductivity value. Okay, so this you need to understand. Now the same thing I'll be able to visualize in the form of a graph. Okay, fine, we'll see what is that. So I have in the graph y-axis, x-axis, I have lambda m on the x-axis, and root C, that is root of concentration, square root of concentration I have in the x-axis. Okay, I will tell you why do I have a root C. You can even just put C, you will see the same kind of graph coming, but there is a reason why do I have this C. I'll tell you later what is this about. Okay, just in a moment I'll tell you. Okay, so anyways, just assume that this is concentration. Okay, right. Now I know as the concentration increases, right? As the concentration increases, mobility decreases, lambda m decreases. Okay, but you will find there are going to be two types of graphs, right? One graph is going to be a straight line like this. I'm assuming that, okay, fine, this is not a straight line. I'll draw a straight line properly. Okay, assume this is a straight line. Okay, you can see as the lambda m increases, sorry, as the concentration increases, the lambda m decreases. That's fine. A normal straight line I have, right? But I can have other type of graph also. The second kind of graph you can observe is something like this. Not a straight line, but a curved line, right? Not a straight line, but a curved line. We cannot call it as a curved line. It's a curve, right? One thing is a straight line. The other thing is a curve, right? Now, what are these two representing is the question. right? Now, please understand this particular straight line is for strong electrolytes, right? This particular straight line is for strong electrolytes, and this curve, what you see, is for weak electrolytes. Okay, strong electrolytes will have a straight line, weak electrolytes will have a curved line. Now, why is it happening like this? Right? First, we have to understand what do you mean by a strong electrolyte? What do you mean by a weak electrolyte? That first we have to understand. Right? It is again coming from the concept of strong and weak acids. Right? Say I have an electrolyte like say AB. Right? Now this AB will give me A plus and B minus. Right? How much this reaction goes to completion? Right? If it is approximately say 100% dissociation is happening, then I will call them as strong electrolytes. Right? But say only 50, like I'm just giving you some random number, say only 50% is undergoing dissociation, then I'll call them as weak electrolytes. Okay, fine. Now what you have to understand is, people, this AB will form A plus and B minus as I add water molecule to this. Like only if I dissolve this electrolyte, say I have a salt, say NaCl I have. Okay, NaCl salt I have, that will not have Na plus and Cl minus ions. Right? Once I dissolve NaCl in water, then you produce Na plus and Cl minus. Please understand. Right? So what you have to understand is, if I go for more and more diluting, then only ions are produced. Right? If I just have the salt, the amount of dissociation, or I can tell like this, dilution is directly proportional to the degree of dissociation. Is it not? That comes from this thing only, because you have to understand that I have to break this bond, and obviously for me to break this bond, some kind of bond has to be formed, and that is given by H2O. Okay, so more and more water you add, more and more is the degree of dissociation, more and more is the number of ions produced, and obviously as the dilution increases, more and more will be the conductivity or molar conductivity. Like say dilution and concentration are opposite terms. Concentrated, diluted. Okay, so more and more dilution, more and more water molecule you add, more and more will be the degree of dissociation, more and more will be the conductivity value or lambda ion value, whatever it is. Okay, now for strong electrolytes, if this AB is a strong electrolyte, as you add more and more amount of water, the A plus and B minus will be continuously forming. It's very fast. The moment you add water, more amount of A plus and B minus. Right? But in case of weak electrolytes, what will happen is, you add water, it is not going to be as efficient as in the previous case. You have to add a lot of amount of water. Say for example, right, say I have AB, right, say now it forms A plus and B minus, right. Say assume that I produced some 100 ions by adding 10 ml of water. Okay, assume that this is a strong electrolyte. Okay, I have a strong electrolyte AB, and by adding 10 ml of H2O, right, by adding 10 ml of water, I produced 100 ions. Okay, but if it's going to be a weak electrolyte, by adding 10 ml of water, say I can produce only 10 ions. Hope you're trying to understand what I'm trying to say, right? So for the same amount of water, 10 ml of water, 10 ml of water only. Right? But as a strong electrolyte means I will be producing 100 ions, but with the weak electrolyte, for the same amount of water, H2O, 10 ml, you will be producing only 10 ions. That is the difference between strong and weak electrolytes. Okay, so obviously you can see for the say, if you keep on adding water, say I'm going from this side to this side, right? This side to this side I'm going. That means I'm adding more and more and more water. Obviously, if this side I go, I'm adding more and less amount of water. It's like that. Right. So as I add more and more amount of water, both of them are increasing. You can see from here to here, it's increasing. Again, from here to here, it's increasing. Right. But the thing is, in case of a strong electrolyte, you add amount of water, there will be lot of ions produced, and that's why it's a straight line. But for weak electrolyte, same amount of water you add, there is going to be lesser amount of ions produced. Okay, and that's why you have a very slow increase, or say when I increase the concentration, there is a slow decrease. But when I increase the concentration, there's a fast decrease, a very rapid decrease in case of strong elements. Okay, and that is why we see two different types of graphs. Okay, fine. Now we'll any questions, guys? Do you have any questions from this part? Whatever I told you now, any questions, any clarity, anywhere required? Anybody has any questions? Okay, I hope everybody understood why is there two different types of graph for strong and weak electrolyte. It's all about degree of dissociation. Okay, for the amount of water molecule, for the amount of water you add, how much is the degree of dissociation? Obviously, for a strong electrolyte, there'll be higher degree of dissociation, and that's why it's very fast decrease. But for weak electrolytes, since the degree of dissociation is very small, there'll be a slow decrease happening in case of weak electrolytes. Very, very simple. Okay, right? Fine. Now we'll understand what is the thing which I have this root C. Why don't I have C? Right? It's because we have when I plot the graph, right? When I plot the graph with C alone, the straight line is not that perfect. Okay, but if I put it with root C, the line which I'm going to get is a perfect straight line, a more of a perfect straight line than when I'm going to use C. Okay, now since you have a straight line, right, I can have an equation for the straight line. I'm talking about strong electrolytes, people. Only strong electrolytes has a straight line, right? So I'm talking about strong electrolytes. Since it's a straight line, I have a straight line here. I can actually get an equation. Okay, now before we move on to see what is the equation, actually, right? So when I extrapolate this graph, like the straight line graph, I keep on extrapolating. Yeah, sorry, this is not. Okay, so when I keep on extrapolating this graph, okay, guys, bear with this. Okay, if I keep on extrapolating this graph, this line will meet, right? This line will meet the y-axis at some point. Okay, this is what is the intercept, is it not? If I keep on extrapolating this graph, this straight line is going to meet the y-axis at some point. Okay, at that point, what I basically have zero concentration. Is it not? The concentration is zero. I can tell that it is zero concentration, or I can tell that it is infinite dilution. Obviously, concentration and dilution are opposite terms, right? So here I have zero concentration, or I would say there is infinite dilution. Okay, now please understand this particular value is a lambda m value at zero concentration. At zero concentration, there is going to be some lambda m value. Okay, now that particular value, right? That particular value is how I represent it as lambda m naught, or I can even represent it as lambda m infinity. Naught represents zero concentration. Infinity represents infinity represents infinite dilution. Okay, and this lambda m naught or lambda m is what is called as, I think I have space, I have here somewhere I can write. Yeah, so this lambda m or lambda m naught is what is called as limiting molar conductivity. What do you mean by limiting? That's the last value. That's the maximum value, or I can even tell this limiting molar conductivity is the maximum lambda m which you can attain for any solution, right? Because you can see from the graph itself, right? That is the maximum value. At zero concentration, whatever the value of lambda m you have, that is what is called as limiting molar conductivity, and obviously that is the maximum lambda m value. Okay, so if someone asks you, how do you define limiting molar conductivity? You should tell them that it is the molar conductivity, right? Limiting molar conductivity is the molar conductivity when the concentration is zero or when the dilution is infinity. Okay, that is how you define it. Okay, fine. So you extrapolate the graph, you get some point on the y-axis, and that point has zero concentration. So whatever be the value of the lambda m at zero concentration is what is called as limiting molar conductivity, which is the letter lambda m naught or lambda m infinity, either of that. Okay, fine. Now actually we can go for the straight line equation. Now you have what to say. You have the x-axis, y-axis, you have the intercept, everything is there. So now actually the line should be what? Y is equal to mx plus c. That should be the normal straight line equation. right? In y-axis, what you have? In y-axis, you have lambda m, right? Now in x-axis, what do you have? In x-axis, you have root c, right? X-axis, you have root c, right? We'll keep m as m. That depends on the electrolyte. So m is the slope, okay? M into root c plus c is the intercept, right? What is the intercept now? Intercept is basically lambda m naught, right? That is the y-axis intercept, right? This thing is lambda m naught. Okay, now this equation lambda m is equal to some slope, this m is slope, into root c plus lambda m naught. This equation is what is called as Debye. Okay, I think it's Debye-Onsager, Debye-Huckel-Onsager. I think there should be Debye-Huckel-Onsager equation. Okay, Debye-Huckel-Onsager equation. Okay, lambda m is equal to m, that is slope, into root c plus lambda m naught. We know what is lambda m naught. Lambda m naught is limiting molar conductivity. Root c is root of concentration. M is the slope. It's called Debye-Huckel-Onsager equation. Okay, now there'll not be any problems on all. Don't worry. You just have to know the equation. That's it. There'll not be any problems on all coming from this, right? And this can be easily attained from the graph itself. What you have done here. Okay, right? Fine. So now, okay, now we have understood what all things about strong electrolytes. Strong electrolytes are very easy to understand. Okay. Now, when you go to weak electrolytes, people, right? Say I want to find what is the limiting molar conductivity of a weak electrolyte. Okay, I want to find what is the limiting molar conductivity of a weak electrolyte. Now, what I did in the previous case, I tried to extrapolate this graph and it met at a point. Right? But if you do that for a strong electrolyte, right, I don't know where this is going to meet. This eventually, ideally speaking, this will never meet. This will never meet the x-axis, sorry, y-axis. Okay, this will never meet the, or I would say it is going to meet at very some point, which I will not be able to, do this efficiently, even though say it's going to meet at some point there, right? Now that point might not be an exact value. Okay, it is very difficult. We cannot just extrapolate the graph to find out the lambda m naught of a weak electrolyte. How we do for a strong electrolyte, we cannot do it for a weak electrolyte. Okay, so then what is the way? What is the way to calculate or to find out lambda m naught of weak electrolyte? Okay, so we are trying to find out lambda m naught of a weak electrolyte. How do we do this? We cannot extrapolate the graph as we did in the case of a strong electrolyte because that is not going to happen. So for me to find lambda m naught of a weak electrolyte or for any electrolyte for that matter, now whatever I'm going to tell you, right, with that particular thing, you will be able to find the lambda m naught of any electrolyte. Okay, and that particular thing which is going to help me is, any guesses since the chapter is completed? Any guesses? Which is what am I going to use here, guys? For finding lambda m naught of any electrolyte, there is one thing which we can use. What is that called as? It's a law. What law? No, I'm asking you this question because this has been taught in your school. That's why I'm asking you, or else I'll not ask you. Anybody remembers what is that law which is going to help me find out lambda m naught of any electrolyte, not only weak electrolytes, for any electrolyte? What is it called as? Okay, I suppose nobody remembers. It's called Kohlrausch's law. Okay, Kohlrausch'. Okay, Kohlrausch's law. Okay, now please take the statement, people. I'm going to tell you the statement. Please take down the statement for Kohlrausch's law. Okay. The limiting molar conductivity of any electrolyte, the limiting molar conductivity of any electrolyte is equal to the limiting molar conductivity of any electrolyte is equal to the sum of the individual ions, or I would say, wait. Sum of, right. So the limiting molar conductivity of any electrolyte is equal to the sum of the limiting molar conductivities of, is equal to the sum of limiting molar conductivities of the individual ions, present in the electrolyte. Sum of limiting molar conductivities of individual ions present in the electrolyte. Okay, that is what is cold process law. So if I can repeat the statement, people, right? So the limiting molar conductivity of any electrolyte is equal to the sum of limiting molar conductivities of individual ions present in the electrolyte. Okay, now what does that say you? The statement is very simple, people. Say I have an electrolyte AB, some electrolyte AB. Okay, and obviously it is going to contain, say, A plus and B minus. Okay, so if I want to find what is lambda m naught of AB, now what it says, the limiting molar conductivity of any electrolyte is equal to the sum of limiting molar conductivities of the ions present. Basically, it's equal to lambda m naught of A plus lambda m naught of B minus. This is exactly what my cold process law says. Okay, so if I have the whole electrolyte, you separate them into ions and you add the limiting molar conductivities of the ions, individual ions, you will be getting the lambda m naught of the whole electrolyte. Okay, right? Now, but you have to be very careful, people. Right? Say if it is a monoatomic, say A plus B minus, A 1 plus A B 1 minus, and I have only one of them, no problem. You'll easily write like this. Okay, but if you have, for example, say lambda m naught of MgCl2, right? Lambda m naught of, or I'll write it like this first. Right? Now, please understand. Say I have AX. AX, I mean, it's black. Okay, so AX BY is my electrolyte. Okay, AX BY is my electrolyte. Now tell me, if it dissociates, what am I going to form? What are the ions formed? Tell me. If it dissociates, what are the ions formed along with the stoichiometric coefficients? Tell me. What ion it will form? Are you guys thinking? Or what? Is there anything in the chat? There's nothing in the chat. What ion it will form? AX, BY if I have. Okay, guys, I think you are getting confused. Now look at this. If I have Al2O3, okay, Al2O3. Now, how did I get this formula? I know aluminium ion forms Al3 plus, oxygen ion oxygen forms O2 minus. Now this 2 will come here, this 3 will come here, and that's how you end up with Al2O3. Correct? Right? Now looking at this and looking at this, can you tell me what will be the ions formed here?
Sir, AY and BX.
A charge. What is the positive or negative? AY what?
Positive.
AY plus
BX minus.
X minus. Absolutely. Okay, this is what is the ion form. Very simple, guys. This whatever is there, that's the valency of A. And this X whatever you have is the valency of B. Okay, but I have to include the number of ions also. Now you see there is X, A and B, B, Y moles of B. So it should be X, Y plus and Y, B, X minus. That's how you write it. Right, it's like say same Al2O3. If I write Al2O3 will give me 2 moles of Al3 plus 3 moles of O2 minus. That's exactly what I'm doing here also. if you're getting confused what I'm doing. Okay, right. So whenever you have these kind of situations, like say this is just mono positive, mono negative, you directly add it. Okay, but whenever you have more than one charge, say though it is not 1 plus, it is not 1 minus, say it is 2 minus, 2 plus, and say it is not going to form only one ion, 1A plus 1B minus. No, say you have X moles and Y moles. Like that, if you there, remember this, the charge value has to be divided, right? And the stoichiometric coefficient should be multiplied. Okay, remember this. Okay, the charge value has to be divided. Divided with what? I'll tell you. And the stoichiometric coefficient has to be multiplied. Right? Okay. Now, if I'll tell you what exactly is this. So if I want to find lambda m naught of ax by, right? Now that is not just equal to lambda m naught of ay plus and lambda m naught of bx minus. No. I told you the charge has to be divided and the stoichiometric coefficient has to be multiplied. Now the stoichiometric coefficient of A is X. So X would be multiplied and charge should be divided. Right? Stoichiometric coefficient is multiplied, charge is divided. So stoichiometric coefficient is X, right? The charge is Y. So it will be X divided by Y into lambda m naught of AX plus again the stoichiometric coefficient multiplied Y, the charge is X divided by X into lambda m naught of dy. Oh, sorry, this is Y plus. This is Y. Sorry, guys. This is Y plus, and this is X minus lambda. This is how you write. Okay, charge has to be divided. You see the charge of A is Y plus, so I divide it by Y. And the stoichiometric coefficient is 2. That means I put X in the numerator. Same way for Bx minus. Okay, maybe if I give you one normal example, not in terms of A and B, then you'll be able to understand. Say I have, what can I give? Lambda m naught of, say I write Mg2 plus. Sorry, MgCl2. Okay, can you represent it in this way? Right, it's equal to something, right? Can you represent it in this way and tell me what you're going to get?
Sir, is it the 1 by 2 lambda m naught Mg2 plus plus
Yeah,
2 by 1 lambda m naught B 1 minus?
Cl minus.
Yes.
Right?
Yeah.
Correct. Yes, correct. What you're telling is correct. Okay. Now it's very easy, right? Now I have MgCl2 giving Mg2 plus 2Cl minus. Very, very important. 2. Okay. So if I want to write lambda m naught of MgCl2, now there is no stoichiometric coefficient, so nothing should be divided, but there is a charge of 2. So it will be 1 by 2 into lambda m naught of Mg2 plus now there is no, the charge is only 1, but there is a stoichiometric coefficient of 2 that has to be multiplied. So 2 into lambda m naught of Cl. Very simple. Okay. Now I hope you all understand what am I doing here. The charge divided, stoichiometric coefficient multiplied. Staying in Mylapore is actually good in so many ways, but you know this background noise is an unending phenomenon. Really sorry, guys. Okay. So yeah, so the charge is divided and the stoichiometric. One second, guys. One second. Okay. Okay. Sorry guys, there was a lot of background noise. Someone selling something. Okay, whatever. Hope you all understood. Charge is divided and the stoichiometric coefficient is multiplied. Very simple. Okay, right. So we'll try to do some problem on this particular thing, what we did now. Okay. See, like questions will be given like this. Okay. Say they will give you lambda m naught of say 2-3 substances. Say lambda m naught of say one substance, second substance. They will give you and they'll ask you to find lambda m naught of third substance. Something like that they'll ask you. Okay. Now you know how to represent them, right? If at all, whatever the component is given, you know how to represent them. Same way you know how to represent the third molecule also. Right? So somehow you have to add these two or subtract these two so that you will be getting this lambda m naught of the third substance or whatever be the number of atoms given to you here. Okay, we'll try to do it. Anyways, I'll give you the problem. You try to do it. Obviously, I'm going to do it after you complete or if you're not able to do it. Okay, fine. I'll give you the problem. One second. Maybe I will take. Just give me a moment, guys. Or no, this one. Yeah, I'll take this. So they have given lambda m naught of BaCl2, write it properly. Lambda m naught of BaCl2 is given as 280 into 10 to the power minus 4 Simon meter squared per mole. Obviously, lambda m naught and lambda m will have same unit, right? This is Simon meter squared per mole. Okay, fine. Next, they have given lambda m naught of NaCl to be 126.5 into 10 to the power minus 4, again Simon meter squared per mole, and lambda m naught of NaOH, right? Lambda m naught of NaOH is 248 into 10 to the power minus 4 Simon meter squared per mole. Now all I need is lambda m naught of BaOH twice is what? Okay, so lambda m naught of BaCl2, NaCl and NaOH is given to you. I need to find what is lambda m naught of barium hydroxide, BaOH twice. If at all you're wondering what is this, BaOH twice. Try to do this problem. Okay, anyways, I'm going to help you after some 2-3 minutes. Right? And I'll be back in a minute, guys. You do the problem, I'll be back in 1 minute. So I told you how to approach the problem. You know how to represent this, how to represent this, how to represent this, as well as how to represent this. Right? So something you have to do so that you will be able to get these two. That is BaOH and OH, Ba2 plus and OH minus. Any answers, guys? Any answers from anybody? Okay. You need some more time, or I can solve. Anybody needs more time? Do you need more time, or I can solve?
So there's 2 minutes.
Sorry. Yes, Nandakishore, you're telling something.
So there's 2 minutes.
Okay, sure. Take it. Yeah, right. Okay, I'll give you, maybe it's 10:44, 10:46. You give me 2 more minutes, and then I will solve. Okay. Any answers? Right. Cool. Maybe I'll solve it. Okay. Right. So now, how do we represent this? Where am I? Yeah. So how do we represent this BaCl2? I can write it as lambda m naught, or I would say first 1/2 into lambda m naught of Ba2 plus 2 into lambda m naught of Cl minus. Okay, this is okay, guys. I hope you understand. Charge of 2 divided, obviously it will give me 2 Cl minus ions, so I multiply it by 2. Okay, so half into lambda m naught of Ba2 plus 2 into lambda m naught of Cl minus is this much value. Okay, same way I'll be able to represent NaCl also, which is very easy. Lambda m naught of Na plus lambda m naught of Cl minus. Okay, same way for NaOH, lambda m naught of Na plus lambda m naught of OH minus. Okay, same way for this, lambda m naught, or I would say 1/2 into lambda m naught of Ba2 plus 2 into lambda m naught of OH minus. Okay, I hope, or at least this part everybody should have gotten correct. Okay, whatever I wrote till now, this part, these parts, for all the 4 electrolytes, how do you represent in terms of Kohlrausch's law? That should be in your fingertips. This all of you should have gotten right. If not, try to know it. How we got it. It's very simple. Charge is divided, stoichiometric current is multiplied. Very simple. Okay, right. Now look at what is required. I require half into lambda m naught of Ba2 plus. Right. Now see, where do I have this? I have it here. Okay, half into lambda m naught of Ba2 plus is there. Okay, now what I need 2 into lambda m naught of OH minus. Right. So first we'll check where is lambda m naught of OH minus. Lambda m naught of OH minus is here. Okay, but what I need is 2 into lambda m naught of OH minus. So what I have to do, I have to multiply this entire thing, like from here to here. This has to be multiplied by 2. Is it not? Then only I will be getting 2 into lambda m naught of OH minus. So what I can understand is, say if I mark this particular equation as 1, this as 2, and this as 3, right? The first step 1 would be 1 plus 2 into 3. Is it not? right? One is I'm having Ba2 plus half into Ba2 plus, that will come as such 1. And I have to multiply this third equation by 2 so that I'll be getting 2 into lambda m naught of OH minus. Okay, now if you do that step, what will I be getting? I will be getting half into lambda m naught of half into lambda m naught of Ba2 plus. Now it is not only that it is there, I even have 2 into lambda m naught of Cl minus. I'll write that also. 2 into lambda m naught of Cl minus. Okay, that's about the first equation. Now you have to multiply the second equation by 2 and then add it. So now what will you have? You will have plus 2 into lambda m naught of Na plus 2 into lambda m naught of OH minus. Okay, now when you add or multiply whatever it is, the lambda m naught value also has to be added and multiplied, right? So after step 1, the whole equation will correspond to 280 into 10 to the power minus 4, right? 280 into 10 to the power minus 4 plus, now what is the value for NaOH? NaOH is 248. So 2 into 240 will become 500. 500 minus 4, which will be 496 plus 496 into 10 to the power minus 4. And that value 280 plus 400 will become 680. 680 plus 90 will become 770. 776 into 10 to the power minus 4 is what we have after this first step. That is equation 1, that is half Ba2 plus and 2 OH minus, that is I require 2 OH minus, so I'll multiply the third equation by 2 and I added it. That's it. Okay, that we got. Right, now I have half Ba2 plus and I have 2 into lambda m naught of OH minus, that is there. But that's what we require. But other than that, I have 2 Cl minus, that is 2 into lambda m naught of Cl minus and 2 into lambda m naught of Na plus. Okay, I don't need this. Okay, so for that, what I have to do, I have to go for subtracting, right? I have Na plus here and I have Cl minus here. So what I can do is if I can multiply this equation by 2 and say if I call this equation as fourth equation, right? Now what I can do, step 2 would be, I don't need this 2 into lambda m naught of Cl minus. I don't need this 2 into lambda m naught of Na plus. So for that, equation 4 has to be subtracted from this second equation, that is 2 into the second equation. Hope you all understand what I'm trying to do. First step is okay, right? Ba2 plus half into Ba2 plus and 2 into OH minus, we got it. But other than that, we got something extra also. We don't need this. All we need is only this, guys. Only this part. Lambda m half into lambda m naught of Ba2 plus 2 into lambda m naught of OH minus, because that is what is asked. But I have something extra also, Cl minus and Na plus. So you have to look at where is Na plus and Cl minus, and depending on the requirement, that is 2 or 3, you multiply it and then you subtract it. Very simple. Okay, so if you do that, what will happen? I will be basically ending up with lambda half into lambda m naught of Ba2 plus 2 into lambda m naught of OH minus. That's it, because this 2 into lambda m naught of Na plus and 2 into lambda m naught of Cl minus will be subtracting with this 2 into lambda m naught of Na plus 2 into lambda m naught of Cl minus. That will be subtracted, gone, cancelled, right? Okay, now if I have to get the overall this thing, so I already have for the fourth equation 776 into 10 to the power minus 4, right? Now I have to subtract it with 2 into this value, 2 into NaCl value, that is 126.5. So 125 would be 250, 126.5 will be 253. Okay, minus 253 into 10 to the power minus 4. And that if you do, it would be 3, this would be 2, this would be 5, 523 Simon centimeter squared per mole is the lambda m naught value of BaOH twice. Where is this? Yeah, lambda m naught of this thing is, how much we got? 523 into 10 to the power minus 4. Okay, so Simon meter squared per mole. Very, very simple, people. All you need is only this. So do something to the given equations. It's like just like thermodynamics, what we solved, delta G, you added, subtracted, something you did. So that you need this, exactly same thing we do here also. Okay, can I get a yes from everybody, guys, if you understood? Everybody understood? Can someone put in the chat box and unmute and say yes? Is it okay, guys? Everybody understood? Okay, one I got. Okay, what about others? Everybody is okay? Just for my satisfaction, again, one more.
Yes, sir.
Okay, so yeah, 3, 4. I have almost 5, almost 9 people. Everybody is doing okay, I guess. Right? Okay, fine. If you're okay, I'm okay. Right? Say, please do not sit idle if you don't understand. Okay, all this, your efforts, my efforts should not go to waste. I'm explaining something. It is okay for you to not to understand. Right? But the problem is you not understanding and keeping quiet. That's the problem. Okay, it's your right to ask. Right? I hope everybody understood what we do here. Okay, we'll do one more problem based on this so that we'll become more comfortable. Okay, but let me see what question do I have. Okay, so they have given lambda m naught of KCl is 149.9 Simon centimeter squared per mole. Okay, and lambda m naught of KNO3 is 145, that is Simon centimeter squared per mole, and lambda m naught of HCl is 426.2, and lambda m naught of CH3COO Yeah,
Sir, what is the value of lambda? I'm not KNO3. I can't understand.
lambda m naught of
KNO3.
oh
I can't
145. Lambda m naught of this is 145. This is 145. Okay, and lambda m naught of CH3COO is 91, and at last lambda n naught of NaCl is 126.5. Okay, now what I need is lambda m naught of CH3COOH. This is what I need. Okay, go for it. You can easily solve it. Very easily. Just follow the steps as we did in the last time, and you are going to get the answer. This problem is easier compared to the previous problem. Yes. Any answers, people? So, like the thing is, you don't need, they're giving you 5 datas, and you don't need 2 of the datas. Can you tell me what are those 2 datas which are not required to me? Out of the 5, only 3 are required, 2 are not required for this problem. What are the 2 data which are not required? Hope you understand my question. The question is, there are 5 data given to you: KCl, KNO3, HCl, C3CON, and NaCl. Out of that, I require only 3. The other 2 are chumma to confuse you. What are those things which I don't
So
require for this problem?
KCl and KNO3.
Absolutely. These are of no use to us, right? KCl and KNO3 are of really no use to us. Okay, the other 3, yes, they only have to be used. I'll give you maybe 2 more minutes, people. Then I will do the problem. 11:05. I will do the problem. Let me see if anybody can give me the answer. Any answers? Anybody has? No answers? I don't know why are you finding it so difficult. It's pretty easy only, right? Okay, fine. Maybe I'll do it. Right. So now for this, how do I represent this? I represent it as lambda m naught of CH3COO minus plus lambda m naught. Just give me a moment, people. Call. I'm sorry, guys. I'm not actually feeling well, so I thought like, next I have 11th class. I don't think I'll be able to take it. That's what we call about. Anyways, so I have this lambda m naught of CH3COO H. I can write it as lambda m naught of CH3COO minus plus lambda m naught of H plus. Okay, let me write like that for everything. And I told you that these two are not required at all, right? So, but we'll just do for the next three. So this can be written as lambda m naught of H plus lambda m naught of Cl minus, and this would be lambda m naught of CH3COO minus plus lambda m naught of Na plus, and this would be lambda m naught of Na plus lambda m naught of Cl minus. Okay, done. Right. Now see what we need. We need lambda m naught of CH3COO minus. See, where is it? Okay, this is where I have lambda m naught of CH3COO minus, and we need lambda m naught of H plus. See, where is it? Lambda m naught of H plus is here. So if I call this equation 1 and this as equation 2 and this as equation 3, right? So first step, right? Step 1 would be to add 1 and 2. Very simple, right? Now, when you add 1 and 2, you will be getting lambda m naught of CH3COO minus lambda m naught of H plus. You will be getting that. Also, you will be getting this particular term and this particular term, that is Cl minus and N plus, and I don't want that, right? Now, very easily you can see, I don't need these two, but I have again Na plus and Cl minus in the third equation. So you can only one step, you can easily get the answer. 1 plus 2 minus 3. That's it. You are going to get the answer. Okay, everybody understood, I guess. I require CH3COO minus and H plus. CH3COO minus is here. H plus is here, and if you add these two, I'm getting extra terms, that is Cl minus and Na plus. Now, obviously, in the third equation, I have Na plus and Cl minus. To subtract it, the only thing remaining will be CH3COO minus and H plus. Okay, so if I just have to add 1 and 2 and subtract 3. So if I add this, right? So 426 plus 91, 426 plus 90 will become 516.2, 517.2, 517.2, 617.2, 617.7, 623.7, 643.7. That would have been the answer. Simon, centimeter squared per mole. Okay, guys, was it so difficult that you're not able to get the answer? How much time it took? 1 minute for me to solve the problem? right? Is everybody okay, people? Like whatever we are doing here, are you finding it difficult? Any problem is there? Or can you tell me why was it so difficult for you to get the answer? Anybody can tell? Easy problem, right? Is there what was the problem exactly? Then I can address it if there's any particular problem. What was the problem, guys? Where did you go wrong?
So for me, the calculation took time.
Calculation took time. There's nothing, right? Calculation is just addition. At least for the last problem, we had to multiply by 2, add, subtract. But this time it's just one addition, one subtraction. That's it, right? Okay. Anything else you faced? Any other problems?
Sir, I got a different answer.
Sorry, Kana, I'm not able to hear. What?
Sir, I got a different answer, sir. Sir,
Different
I think
answer.
you added all the three, sir.
Oh, yes, absolutely true. Correct. Yes, I added all the three. So the answer is wrong, guys. But anyways, it's not about the answer. Forget it. Right. The other parts, the calculation part, other than the calculation part, these parts and all should be very easy to you. That writing the Gold-Ross's law part and all should be very easy to you. Right. Is there any other problem you faced in this kind of problems? Because for all the other types of problems from the previous class, I have at least got 1, 2 answers. But this problem, this kind of problem, I think you're facing some difficulties. You can let me know whatever it is, and I can address accordingly. And any problem, guys, any specifically you're facing anything? Okay, I suppose if at all you found anything, this thing, I think when I explained, I think that should be clear how exactly you should do it. Okay, fine. That's it for today. Okay, so we'll see you again next week, guys. Okay, I hope there are no questions. Everything is clear. If there's anything, you can always personally text me. You all know that, right? I'm going to stop here. Right? Okay, thank you so much, people. We'll meet again next week. I'm going to end the class.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Yeah.